Welcome back to Shmeshpre. This video is part of a series where I build math from the ground up, starting from set theory. I'll link the full playlist in the description, so go check it out if you're not up to date. So far, we've built some intuition about what sets are. We saw how we could depict sets as containers, where the contents, its elements, are other sets. But I warned you not to take this analogy too literally, since unlike with containers, if one set lies inside another, the elements of the inner set are not necessarily elements of the outer set. Here the empty set is in both, and we draw it twice, once in each, but this set is only in the inner set, not the outer set. We saw that a way to depict sets that's somewhat truer to what they really are is to consider them as part of a network, with connections telling you which sets are elements of which other sets, and these networks must satisfy a list of rules. We want to pick our rules so they align with our intuition for sets, which we can still get from this depiction of sets as boxes, as long as we remember its limitations. Last time, we introduced logic, including all of these symbols, so now we have the language we need to finally present these rules, which are called the axioms of ZFC. Sir Mello-Frankel's set theory with the axiom of choice. Without further ado, let's take a look at these rules. Our first rule is the axiom of extensionality. This tells us that if two sets have exactly the same elements, then they are in fact the same set. That is, they are equal. Why is it called the axiom of extensionality and not, say, the axiom of equality? I have no idea. Now let's look at the formal statement of this axiom. This is a good time to go watch my video on logic again for a refresher, because we're going to need the symbols and terminology I introduced in there now. Here it is. For every set A and every set B, if for all C, C is an element of A, if and only if C is an element of B, then A equals B. It's okay if you need to pause and ponder to figure out how to read this expression, rewind a few times, or come back another time to dissect it. This, of course, also applies to the rest of the rules coming up shortly. Next, the Axiom of Union. This tells us that given any set of sets, we can form a set which contains every element of each of those sets. Essentially, we can dump out each of these sets into a new set. Here's the formal statement. For every set A, there exists a set B, such that for every set C, if C is an element of A, then for all D, if D is an element of C, then D is an element of B. Note that as I've phrased it here, the set B might contain other elements besides just the contents of the sets in A. But another one of our rules will allow us to filter out the junk. A little warning here. I'm taking advantage of the other axioms to phrase these axioms as simply as possible. If you want to study what happens if you remove certain axioms, you may need to phrase the rest differently so they still mean what you want them to. So for example, if we wanted to work in set theory without the rule that lets us get rid of this extra junk, we might want to modify the axiom of union to add the condition that there is no extra junk. Next, the axiom of power set. First, if A and B are sets, we say A is a subset of B if every element of A is also an element of B. The axiom of power set then tells us that given any set, we can form a new set which contains every subset of that set. Now for the formal statement. For every set A, there exists a set B such that for every set C, if for all D, for which D is an element of C, we have that D is an element of A, then C is an element of B. Again, there may be extra junk in there, but we can filter it out later. Note that the axiom of power set doesn't tell you these subsets exist. For instance, before we can show that this new set we get contains a set like this one here, with just a yellow square and a red circle in it, we'd first have to show, using our other axioms, that this actually is a set. In principle, there could be subcollections of a set that don't happen to be sets themselves, and those aren't included in the new set we form. Next, the Axiom of Infinity. This tells us there exists an infinite set. Well, we'll define what it means for a set to be infinite eventually, but the definition is rather involved, so instead, we're going to require that there exists an infinite set of a particular form that's easier to state. This turns out to be equivalent to just asking for an infinite set. Specifically, we're going to require that there is a set which is non-empty. The first step towards having infinitely many elements is having at least one element. And for every one of the elements of this set, there is another one of its elements which contains the first element. And then, of course, it follows that there's another element that contains that one, and so on. That's how we get an infinite set from this. Let's look at the formal statement. There exists a set A, such that there exists B, such that B is an element of A, and for all C, if C is an element of A, then there exists D, such that D is an element of A, and C is an element of D. There can be other elements of this set that aren't part of this chain, but they'll form a chain of their own. Well, in order for this to actually give us an infinite set, we need that these chains don't loop back on themselves. For example, if this yellow circle somehow contained this set here. That will be our next axiom, the axiom of regularity. This tells us we can't have a set with infinite chains like this going in the opposite direction. We can have an increasing chain of sets, but never a decreasing chain of sets. Where by increasing, I mean each object in the chain is an element of the next, and by decreasing, I mean that each object in the chain has the next as an element. So it's a bit stronger than just ruling out chains that loop back on themselves. We rule out infinite chains too. Well, there's a slight caveat to that, which I'll get to shortly. Anyway, this axiom states that every non-empty set has some element where this chain ends, meaning that none of its contents are elements of the larger set. Now the formal statement. For every set A, if there exists B such that B is an element of A, then there exists C such that C is an element of A, and for all D, if D is an element of C, then D is not an element of A. Note that this doesn't rule out sets with an infinite decreasing chain like this, that contain other elements, like this one, that don't form part of such a chain. Our next rule will allow us to improve the situation somewhat by often, but not necessarily always, allowing us to filter out certain elements of our set to remove dead ends like this, so that regularity can rule out the set for good. Specifically, this next rule tells us we can refine the elements of a set by filtering out everything we don't want and replacing the remaining elements with what we actually want. This is our axiom schema. It's not a single axiom, but a rule which generates axioms. In fact, it's usually stated as two different axiom schemas, one called the axiom schema of specification, and the other called the axiom schema of replacement. Specification does the filtering out of elements we don't want, and replacement lets us replace the elements with the ones we actually want. But it's not too hard to combine these into a single statement, so that's what I'll do here. I'm going to call this the axiom schema of refinement. This name is entirely my own, but if anyone knows of an existing name for this axiom schema, let me know in the comments. Let's fix a set and suppose we have a predicate in two variables, a property that a pair of objects might obey. These objects are sets, but we don't really care at the moment. We're actually going to need a predicate in 3 variables for the proper statement of our rule, but only 2 of them will play an important role, so we won't bother with that just yet. Anyway, we have a property that a pair of objects might obey, and we can depict which pairs of objects have this property with an arrow pointing from the first to the second. We only need to draw the ones where the first object is an element of this set we've fixed. We don't care about the rest. These arrows relate the elements of our set to certain other objects, perhaps one, perhaps multiple, or perhaps none. Refinement tells us we can form a new set such that for every element of our first set which does relate to some object, at least one of the objects it relates to lies in the new set. You can double check that every shape in the first set is pointing at least one circled shape, except for the one with no arrows coming out of it. And these circled shapes are the ones lying in the new set. Moreover, we'll require that for every element of the new set, there is some object of our original set which relates to it. So this time, we can't have any junk. To apply this axiom schema, you have to be able to describe this relationship between the objects of our set and those we could replace them with in the language of logic, using a predicate. Sometimes this is easier said than done. Let's see the formal statement, but I'll warn you, this one is quite complicated. We fix a predicate P in 3 variables, A, C, and D, and we require, for this rule to apply, that the variables B, E, F, and G are not yet introduced. Here's our axiom schema. We get an axiom for every such predicate P. Before I unpack it, let's note that this P is a predicate in A, C, and D. So this is the statement that the trio A, C, D, in that order, has the property P. Here, we replace D with E, so this is the statement that the trio A, C, E has the property P. And here, we replace C with G and D with F, so this is the statement that the trio A, G, F has the property P. Okay, but what does it mean that, say, the trio A, C, D has the property P? It tells us C is related to D by this property. Here A is just along for the ride and stays the same throughout. Similarly, this says C relates to E, and this says G relates to F. Okay, let me make some room so I can bring back the pretty picture. You can rewind if you need to see these assumptions again. Our axiom schema states that for every set A, there exists a set B such that for all C, if C is an element of A, and there exists D such that C relates to D by the property P, then there exists E such that E is an element of B, and C relates to E by the property P. And moreover, for all F, if F is an element of B, then there exists G such that G is an element of A, and G relates to F by the property P. We get the axiom schema of specification as a special case of refinement by relating the elements of our set we want to keep to themselves and not relating the elements we want to remove to anything. Then the axiom schema of refinement gives us a set with just the elements we wanted to keep. This is the rule that lets us prove that a subset with particular elements exists, as long as these elements are describable in the language of logic, and that this subset thus lies in the set given to us by the Axiom of Power set. It's also the rule that lets us filter out the dead ends that prevent regularity from working as you might expect, again, as long as these dead ends are describable in the language of logic. The axiom schema of replacement is the special case of refinement where each element of our set relates to exactly one object. Finally, the axiom of choice. The rules we've seen so far are the axioms of Zermelo-Fraenkel set theory, ZF for short, which was developed by Ernst Zermelo and Abraham Fraenkel. Adding the axiom of choice gives ZFC. The axiom of choice tells us that given any set of sets, such that all of the sets it contains are non-empty and have no elements in common, we can form a new set that contains exactly one element of each. Again, there may be some other junk, as long as it's not an element of any of our original sets. The formal statement of this axiom is quite long, so take a moment to ready yourself. Ready? Here it is. For every set A, if for every set B, for which B is an element of A, we have that there exists C, such that C is an element of B, and for every set D, for which D is an element of A, and there exists E, such that E is an element of B, and E is an element of D, we have that B equals D, then there exists a set F, such that for every set G, if G is an element of A, then there exists H, such that H is an element of G, and H is an element of F, and for all I, if I is an element of G, and I is an element of F, then I equals H. Those are all the rules for sets. Let's summarize what we've seen by coming up with a catchphrase for each axiom, telling us what the axiom means, loosely speaking. The axiom of extensionality tells us that if two sets have the same contents, then they're the same set. The axiom of regularity tells us that sets are built from simpler parts. These two axioms are there to make sets more closely match our intuition of them as collections of objects. Two collections are the same if they collect the same elements. So this should also be true for sets. We compare sets by comparing their elements, and we compare those by comparing their elements, and so on, looking at simpler and simpler sets until eventually we reach an end. The axiom of infinity tells us we can start with a big set, an infinite set, from which we can build other sets. The axiom of power set tells us that given a set, we can collect all sets containing a portion of its contents into one bigger set. The axiom of union tells us that given a set of sets, we can dump out their contents into a new set. The axiom schema of refinement says you can swap junk for what you really want. You can replace the elements of a set with others of your choice and get rid of everything else. Finally, the axiom of choice tells us if certain objects exist, you can have one of each. We know from our rules of logic that if one thing exists, we can assume we have one. But the axiom of choice lets us do this for an infinite collection of things all at once. I want to suggest an alternate catchphrase for the axioms of power set and union, but it will take us a while before we can justify this. If the axiom of infinity tells us we can start big, then the axiom of power set tells us we can get bigger, and the axiom of union tells us we can keep going. Together, these axioms allow us to build bigger and bigger sets, and then refinement lets us create the sets we actually want by replacing and filtering out the junk. We saw previously that Russell's paradox prevents us from always being able to create the set of all sets with any statable property we want. But refinement allows us to do so as long as the collection of sets with that property isn't too big to be contained in a set. And sets can get really big. I still have a few loose ends to tie on logic that didn't make it into the last video, so that's what I'll do in the next one, along with some examples of proofs to familiarize ourselves with them a little more, before we finally get into the basics of sets and what you can do with them. See you next time.